Team GChem, and welcome to today's lecture. Today, we're going to be talking about how to determine both empirical and molecular formulas based on experimental data. So last lecture, we talked a lot about how to do unit conversions related to chemical compounds. We talked about how to calculate the molar mass of a compound based on information from the periodic table, and we talked about how to perform gram to mole conversions. Both of these concepts are going to be used heavily in today's lecture, so if you're feeling a little bit of rusty, now's a good time to pause this video and go back and practice those two skills. Otherwise, today's lecture goals are threefold. First, we're going to learn how to calculate the empirical formula of a compound, assuming that we have some information about the masses present of different elements in a compound. Sometimes that may be given to us as raw numbers, or sometimes it might be given to us in terms of percent moles. Either way, we're going to see how that information can be used to calculate empirical formula. The second lecture goal is that we're also going to talk about how if we know the molecular mass of a compound, we can not only determine the empirical formula, but we can also determine its molecular formula. And then last but not least, we're going to do a little bit of a challenge and talk about how it is that chemists actually go about calculating empirical formulas of compounds in real-world experiments. And namely, they're based on the results of what's called combustion analysis. So with that, let's go ahead and get started. All right, so let's start off talking about mass or percent mass and how that relates to empirical formula. The key idea here is that chemical formulas represent the relative amounts of elements in the compound. In other words, just knowing that the formula of CHCl3, which happens to be chloroform, means that we know that for every 1 mole of chloroform, we have 1 mole of carbon atoms, 1 mole of hydrogen atoms, and 3 moles of chlorine atoms. And so this formula tells us that there's a 3-to-1 ratio of chlorine to carbon and a 1-to-1 ratio of carbon and hydrogen. And so the strategy whenever we're doing these sorts of empirical formula calculations is always to figure out how many moles there are of each element. And then from there, we can figure out the molar ratio, which is another way of saying we figured out the empirical formula. So let's watch this process in action by way of an example. So let's suppose that we have a sample of an unknown compound, and what we know about this compound is that our sample has a mass of 50 grams, and of that 50 grams, 39.9 grams of it is carbon, and the rest of it is hydrogen. And we want to figure out what the empirical formula is of the unknown. The first step in this process, I think, is to notice that 39.9 plus 10.1 gives us 50 grams. And so we don't need to worry about there being elements present in this compound aside from carbon and hydrogen. And so we're starting off in grams, but like I said before, an empirical formula is a mole-to-mole ratio. So for us to make progress in this problem, we're going to have to start by converting grams of each of the substances to moles. So let's watch that in action. For carbon, we can see from our periodic table that a mole of carbon atoms is equivalent to 12.01 grams. So if I want to do a grams to moles conversion, I'm going to use my starting amount of carbon, that's 39.9 grams, and I'm going to remember, again, based on information from the periodic table, that for every 12 grams of carbon, I have 1 mole of carbon. And if you like, it's good to remember that we're talking about carbon atoms, not some sort of molecule that has multiple carbon atoms. So just straight up carbon, no subscripts. If I type this into my calculator, I figure out that there is 3.322 moles of carbon that's present in this 50-gram sample. Now, you'll notice for now, because I'm not at the final step of my calculation, I'm not rounding this number based on sig figs. I'm just turning out what my calculator says. And later, when we finish off this problem, that's where we'll consider sig figs. But for the intermediate steps of a problem, it's always fine to have more digits in your intermediate numbers than you really need to help you avoid rounding errors. All right, so we'll do the same thing for hydrogen. In this case, I'm going to start off with my 10.1 grams of hydrogen. And based on the information from the periodic table, which tells me that there's 1.008 grams of hydrogen for every 1 mole of hydrogen, I can submit this information, plug it into my calculator, and determine that the number of moles of hydrogen present in this compound happens to be a little greater than 10 moles. And so if you like, we can sort of write our empirical formula already at this point. What we would say is that our empirical formula is C 3.322 H 10.0198. And while that's technically correct, it does tell us the balance of, or the relative amounts of carbon and hydrogen. Chemists are used to reporting empirical formula in terms of small whole number fractions. And so our next step of this process is mostly going to be to clean up this result to try and figure out what the smallest whole number ratio is going to be. There's lots of different ways to figure this out, but I would say the easiest is to take whatever is the smallest number that shows up at our current stage of the calculation in terms of number of moles and divide all of the subscripts by that amount. Again, because the empirical formula is just telling us a mole-to-mole ratio, it doesn't really matter if we divide all of the number of moles by the same quantity, because that doesn't change our mole-to-mole ratio. So here, if I divide by the smallest whole number ratio, I end up with C1, and then I also end up with H 3.016. And you'll notice that's really close to simply CH3. And because all of these experimental determinations of empirical formula have a little bit of uncertainty or perhaps a little bit of inaccuracy in them, it's pretty safe to assume that in this case, the actual empirical formula is simply CH3. And so that would be our final answer. Again, the steps that we did to complete this problem was first, we determined the number of moles of each element that was present. Secondly, we computed the mole-to-mole ratio. And then third, we simplified. First by dividing by the smallest number of moles, and then by rounding slightly. It takes a little bit of trial and error practice to figure out how much rounding in these empirical formulas is too much rounding. But in general, if you are close within, say, 0.1 of an integer number, that's normally when it's safe to simply round up or down. If you have something that's more like CH1.5 or CH1.33, that's when you start to think that maybe we don't have one carbon in this empirical formula, but I should multiply by a small number in order to get rid of the fraction. Our next example will help us practice that, so you'll see what I mean in just a moment. All right, so here's a second example. By mass, an unknown compound containing solely nitrogen and oxygen is determined to be 25.94% nitrogen. Could the substance be dinitrogen pentoxide? Explain why or why not. So in this problem, you'll notice that instead of being given mass in terms of grams, we're given percent mass. Furthermore, we're asked a question about whether or not a certain empirical formula is plausible, which isn't necessarily the same thing as having to figure out on our own. However, we'll see in this problem that it's easiest to figure out whether or not this could be dinitrogen pentoxide by solving the problem very similarly to how we did in the previous example. So first things first, hopefully we're starting to get comfortable with our chapter 2 nomenclature, and we're able to identify that dinitrogen pentoxide is N2O5. And so that's the molecular formula for this molecule that we're going to ultimately be comparing to. The next thing we have to understand is that when we're talking about percent masses, the masses have to add up to 100. And so because I know this compound is purely nitrogen and oxygen, that means that whatever's not nitrogen in this compound has to be oxygen. And so I know that I have 25.94% nitrogen, and 100 minus 25.94 tells me that in fact I have 74.06% oxygen. Now, when you're starting with percent masses, there's a number of ways that you can go about converting ultimately to moles. Personally, I find the easiest way is to assign a certain mass to my sample. Again, these empirical formulas are sort of intensive quantities. Just because I double the size of my sample or talk about a 60-gram sample versus a 90-gram sample, hopefully that's not going to change the actual chemical that I'm dealing with. And so I can arbitrarily choose some mass of my overall sample in order to help me think through the problem. And it turns out the easiest number to use is 100 based on how percents work. So if I have a 100-gram sample, and again, I'm assuming this for convenience because the math is going to work out regardless of how much I want to think about my sample weighing. And 100 grams is going to make the math way easier. If I have a 100-gram sample, well, that means that 25.94 grams of it would be nitrogen, and similarly, 74.06 grams of it would be oxygen. Now that I have these masses in terms of grams, the previous strategy that we use for determining the empirical formula is going to work just fine for us. I'm going to start off with a mass to mole conversion and then use the mole to mole ratios in order to determine what my empirical formula should be. Go ahead at this point and pause the video and see if you can figure this problem out on your own. And in just a moment, I'll walk you through it in case you get stuck. All right, so for my nitrogen portion of the sample, how I convert grams to moles is I start off with my 25, almost 26 gram sample. And looking at my periodic table, I see that there is 14.01 grams of nitrogen for every 1 mole of nitrogen. Plugging that into my calculator, that translates to about 1.8515 moles of nitrogen. We do the same thing for oxygen. We figure out that the 74 grams of oxygen, again, using information from the periodic table to figure out what my gram to mole conversion should be, means that in total, I have 4.629 moles of oxygen. And so once I've written down this empirical formula, give myself a little bit more space, I can then say that my empirical formula is N 1.8515 O 4.629. Again, it's messy, so I want to clean that up by dividing by the smallest number that shows up in this empirical formula. That gives me a mole to mole ratio of NO 2.5000. And this is the moment in which I need to understand that probably rounding down to 2 or rounding up to 3 assumes far too much experimental error in the formula. And instead what I should do is notice that 2.5 is equal to 5 halves. And so to get everything in this mole-to-mole ratio, to be small whole numbers, I should actually multiply by 2 and get a formula of N2O5. All right, so now that we've done that, we can go ahead and answer our original question that was posed to us. Namely, could this unknown compound be dinitrogen pentoxide? And what I would say to that is that we have found data that is at the very least consistent with this compound being N2O5 because we have an empirical formula that's N2O5. However, I would not say based on this information that we know for sure that this compound is N2O5 because again, the true molecular formula of this compound could be any integer multiplier of this. So we could have a molecular formula of N4010 or N20O50. It seems a little implausible, but still, we don't have enough information to know for sure whether or not this compound is truly dinitrogen pentoxide. And so knowing the empirical formula is useful, but more information would be really helpful to us. And so with that, we can transition to talking about molecular formulas. So the key idea in thinking about molecular formulas is that if we want to find a compound's molecular formula, to go beyond just the empirical formula, we need to have additional information. And that key piece of information that we need is to know the compound's molar mass or molecular mass. And we need to figure out its empirical formula. So all the work we did in determining empirical formulas is really useful. We just now need to know how to take into account a little bit of extra information to figure out the molecular formula. And so a kind of fun fact is that in the previous lecture, we talked about how mass spectroscopy is a commonly used technique to understand what masses there can be for different atoms, where the mass tells us about the different types of isotopes that might be present. Your fun fact of the day is that mass spectroscopy is also a really commonly used technique for determining the molar masses of compounds. So instead of ionizing an atom, we can ionize the molecules, send them through the mass spectrometer, and determine, based on what their weights are, what the molar mass of the compound has to be. Kind of neat. So let's, again, try and figure out the molecular formula and walk through the steps by way of example. So in this example, let's suppose that the hydrocarbon from above, which remember we just determined its empirical formula was CH3, let's say that it's subjected to a mass spectroscopy experiment, and the results of that experiment indicate that the unknown compound has a molecular mass somewhere around 30 grams per mole. From that information, let's determine the chemical identity of the compound. All right, so first things first, step 1 is to determine what I like to call the empirical formula weight. It's basically like the molar mass, except based on whatever your empirical formula is. I'm going to put this in quotes because this is not a technical term so much as what I like to refer to it as in my head. So in this case, CH3 has a molar mass of 1 for the 1 carbon atom times 12.01 grams per mole plus 3 times the molar mass of hydrogen, which is 1.008 grams per mole. Add that all up, and we get that this compound, the empirical formula, has an empirical formula weight somewhere around 15 grams per mole. So the second step of this is that we need to compare the so-called empirical formula weight to whatever the molecular formula is going to be. And to do this, there's kind of one of two strategies that you can employ. One strategy that's perfectly reasonable is that you could notice just by, intuition and eyesight that the molecular mass of the real compound is about twice as big as that of our empirical formula weight. And that might lead you to believe that our empirical formula multiplied by 2 would give us the correct molecular mass. And if you do guess and check, and you determine a compound that has the correct empirical formula and has a molar mass that matches that of what's been experimentally determined, then great, you've solved for what the molecular formula is. So in this case, indeed, if you suppose that your compound, by guess and check, is twice as heavy as CH3, so if we guess that it's C2H6, and you determine its molecular mass, you'll figure out that it is indeed about 30 grams per mole. So that checks out. That's one way that we can know that the compound is C2H6. The other way that we can determine this, maybe a little bit more systematically, is by realizing that the molecular weight divided by the empirical formula weight tells us what integer we need to multiply by in order to get our molecular mass. So in that case, we would do 30 grams per mole divided by 15 grams per mole. That equals 2, which implies that we need to have 2 times CH3 for our molecular formula, which equals C2H6. So once again, we get the same answer to the problem, and you can choose for yourself whether you like this guess and check approach or the more systematic way better. In either case, let's remember that C2H6 is the name of a chemical compound that we discussed in Chapter 2, and in fact, this is ethane. All right. And so last but not least, we want to talk today about combustion analysis and empirical formulas.